So thanks for sticking around to the end of the day. Must be tired by now. How many users of Kafka do we have in here? Okay, a lot. Okay, that's going to make this much easier. So I'm going to tell you about exactly what semantics in Kafka. This is a new feature that we've added in 0.11, which was released only a couple months ago. So like, what does it actually mean, and how to use it? So let's, who am I? I'm Jason. I'm an engineer at Confluent. I'm also an Apache Kafka committer. We were the team responsible for bringing exactly one semantics, but we weren't the team that actually originated the idea. So this has been in the works for a long time. It goes back to LinkedIn days, for example, when Kafka was run at LinkedIn. So brief overview of the talk. I'm going to just give an overview of Kafka just at the level that we need to understand in order to talk about exactly one semantics. So I'm going to cover a very high-level overview. Then we're going to talk about the old semantics in a little bit of detail, just so we can understand where exactly they break down. And then we'll discuss exactly one semantics in some depth. And finally, yeah, if there's enough time, we'll go on to observations and some areas for future improvements. Very briefly, since we have a lot of Kafka users here, I'm not going to dwell on this. Kafka is like a central nervous system for where your data is passing. So we like to say all streams lead to Kafka. It sort of is true. As soon as Kafka's in your architecture, then all data goes through it. So you publish data to it, you subscribe data from it, and you process data on top of Kafka. Kafka organizes data into topics. Topics are organized into partitions. So partition is kind of like the unit of state that we're able to move around the cluster. And the fundamental data structure of a partition is this log of messages, which is we have this sequential offset. As messages are added to it, they get assigned an increasing offset. And very briefly, we're going to spend a lot of time in this talk looking at the log because it's really the best way to understand what is happening inside of Kafka. A log message itself consists of offset, key, value, timestamp, and headers. That's a new feature. For the most part, we're not concerned with most of those fields. We'll focus on the offset and maybe mention other fields when we need them. But for a large part, we'll kind of go with this simpler representation of the log. So as I mentioned before, partitions are the unit of state. So partitions are replicated among the brokers. You can have as many replicas as you want, typically 3 or 4. And then one of those replicas is basically assigned as the leader. And so this is how we get our durability and availability. So the leader fails, one of the replicas is promoted. So Kafka clients, there are 2 kinds. Producers write to partitions, consumers read from partitions or topics, if you want to look at it that way. Let's just understand very quickly how the producer works. So producers, as I said, they're always writing to the leader. The leader is replicating to the follower. And the producer is typically writing to multiple partitions. This replication is happening all the time. You have many producers writing to the logs all at the same time, and you just kind of proceed this way. So in the case of a failure, we have one of the other replicas becomes the leader, and all requests are routed to it. And once the old broker comes back online, it comes back online as a follower. It catches up, and then in order to try to keep the balance on the overall cluster, it will become the leader again, and then we resume. So there are a couple, from a protocol perspective, the Kafka protocol is very simple. It's a request-response protocol. There's one point about the produce protocol in particular that I want to mention because it pertains to semantics. So we have just a very simple produce request, which is received by the broker. We write to the log, and depending on the semantics that you want from the producer, replication may happen before we return. But in any case, we write to the log, and then we get some kind of acknowledgement. It can happen that you fail to get that acknowledgement, in which case typically the producer is going to retry. And retrying, and we'll talk about this more in depth, but you can see this kind of a protocol limitation. It results in duplicates in the log. Okay. So Kafka consumer, so consumers read sequentially from the log, from the partitions, and it kind of works like this. They're reading sequentially. Once you hit some kind of a stable point, you write your position to another topic, this consumer offsets topic, and if you fail, this is where you're going to look for your beginning position. And typically, the nice thing about Kafka, and the reason why it's so successful, is you can have many consumers all consuming from different points in the log, all at their own pace, and all committing their own offsets and whatnot. The protocol, just want to mention this really quickly. There's two APIs that the consumer uses from a basic level. That's offset fetch. This is where I look up what the current, the last committed offset is. And so it typically looks like this. I look up what was the last committed offset. It's X. Then I start fetching from X. And I get data back, process it, and then the offset commit is where I write that to the log. So the main point is really just that there's a separate API for writing to the log for this offset commit. So in order to talk about semantics, we need some kind of a model. This is going to be pretty informal. But basically, the model we have in mind is this read, process, write. We have input topics where we're reading from and output topics where we're writing to, and some kind of processor which is transforming the input into the output. We are interested in a couple different kinds of failures, so our semantics should protect us in spite of these kind of failures. So crashes, if the process crashes, we should be able to recover, and our delivery semantics should be preserved. And similarly, zombie, so in some cases, like a long GC or something like this, if a process comes back to life, even though we thought it were dead, our semantics should still protect us. So let's talk briefly about the semantics that are possible. It's not comprehensive, but this is sort of the typical few. At least once, this is the default in Kafka, and it's what was only possible, or the limits of what was possible in Kafka prior to 0.11, and it basically means that all input is processed and the result is reflected at least once in the output. So it means there could be duplicates. At most once, it's kind of weird, but it means you can accept some message loss, but you just don't want duplicates. It's mostly useful to talk about for pedagogical purposes. Then exactly once, this is kind of what you really want. If you've got a processor which is just copying the input to the output, and you got n messages on the input, you want n messages on the output, and you want them in the same order. There's some theoretical work, two generals problems and whatnot. We're not disproving any of that. I think as this talk goes on, it will become clear what is actually possible and what the limitations are. There's one assumption, though, that I just want to mention. So we do assume that, as far as topic availability is concerned, so topics may be unavailable for some amount of time, but we assume in the long term, eventually they're going to become available. So let's go into this at least once semantics a little bit. This is some pseudocode which should give you an idea of how the consumer and the producer will work together. So we've got, this is not actual code, it's just pseudocode, but let's just walk through it really quick. So we have a subscribe API, which is where you express interest in the topics that you want to consume. You poll, so poll is where you get the actual data. That's where the fetching is happening from the current offset. The consumer is maintaining your position in the log for you. You do some processing of some kind. It's just kind of what Kafka Streams is doing. Then you send that output using this API. And finally, once you do that, you commit offsets. It's not really much of an exaggeration to say that I've spent most of the last 2 years thinking about what happens in send and in poll. So for this talk, I want to condense this a little bit. So we're going to go through a few examples where we discuss exactly where, in at least one semantics, duplicates can emerge. And for this, the processing is not too interesting, so we're just going to copy input to output. So we have this very simple loop right here. So the input in this case is just a sequence of increasing numbers, which we're going to copy to the output. For simplicity, we're just going to copy one message at a time. So yeah, what this looks like, when we start, we're pulling for data, we send it to the output, commit our offsets, and then we continue. So what can happen, we mentioned that the producer protocol is not safe because of this issue with retries. So what can happen is you lose that acknowledgement, you retry, okay, now I've got a duplicate in the log. Okay? And we commit offsets like normal. The second problem that can happen is you send successfully to the topic, and then you have a crash. So in this case, when you resume, you're going to pull from the latest committed offset, which in this case is 2, which means the next message we need to consume is 2. And we're going to have another duplicate. Okay, and then finally, there's one more. This is a little bit more subtle. But we may have fetched some data, and then suddenly we have some kind of system event that causes us to hang. And it hangs for a while. Eventually, we decide that we need to start up another process to continue the same work. So we do so, and we continue like we did before. And then suddenly, our old process wakes back up and sends data to the log. Okay, so there's another source of duplicates. So just briefly summary, duplicates come from producer retries, failure before committing offsets, and zombies. So at most one semantics, I just want to cover this quickly. All you really do in Kafka, if you want at most one semantics, is change the order of those 2 operations. So what it kind of looks like is this. You commit your offset first, then you send the data. You commit your offsets. So we mentioned that producer retries are not safe. You can have duplicates that way. So if you really want at most one semantics, you can't retry. So in this case, if you lose the acknowledgement, oh well, you just go on. The other thing that can happen, so you commit your offsets, and then suddenly we crash. We restart. Well, we lost that message. Okay, and then finally, the last thing, yeah, we can have another zombie case. So we're just about to write data to the log. We become a zombie. Then we start a new process.
Does it have to fail earlier than that before you commit your offsets?
Let's save the question for the end, please. Okay, so in this case, we continue processing some data. Oops, sorry about that. When the zombie wakes, it can send that data. So yeah, your question is about where specifically did you become a zombie? So it can happen basically anywhere. So it could be internal to the producer, for example. We had already processed the data, go into the producer, it experiences some kind of GC event or something like this, and then finally when it wakes up, it sends that data. Okay. So in summary, it's kind of similar to at least once. Retries are not safe. Failure before writing the data, and zombies can cause kind of strangeness. So semantic weaknesses, if we want to summarize them. So producer retries not safe. The process data is not written atomically with the corresponding offsets. So this is the weakness in both of those cases. Are you guys hearing that? Yeah. Yes. Do you know what the cause of that is?
No, that's all off.
Okay, we'll try again.
Should be okay.
Okay. Okay, and then finally the last issue is that we don't have protection from zombies. Okay, so let's deal with the first one, the first problem. So this is actually the easiest one to address. What we do is we introduce what we call the idempotent producer. Basically it's a sequence number. So we identify a producer instance by a producer ID, and then we have a sequence number, which is used to deduplicate. So in the producer, if you want to enable this, you just turn on this flag, enable.idempotence equals true. So how does this work? We'll go through an example just very quickly. So you're producing data with a sequence number, particular producer ID and a sequence number gets written to the log. As long as you write with the next expected sequence number, it will be accepted. Now, if we happen to lose the ACK, we retry, and now we can detect a duplicate. OK, so now we made producer retries safe. The next problem takes a little bit more work to solve. How do we make the writing of offsets and the data atomic? So for this, we look at this. So the motivation for this comes from a little bit of a different problem, which is computing a consistent snapshot in a distributed system. So we have this CHANDY-LAMPORT paper. This is going to be an oversimplification of that paper, but it should convey the basic idea. So we've talked a lot about this processor. Of course, we're processing this data intending for it to get consumed by someone. So we have an observer from the CHANDY-LAMPORT perspective. Okay, what we want to do is think about these output topics as basically a channel that the processor is using to communicate with the observer. And the question that the observer is asking, how can I see a consistent state of the processing? So the processing is going along. We're computing state internally, and we're writing asynchronously to all of these, to the output partitions. And the observer is reading asynchronously, so it wants to know when it's hit some kind of a stable point where it can report data to the user, for example. So the way this works is the processor is writing data to the log, and then when it's ready, when it's reached some kind of consistent point, it writes these marker messages to the log. So like the snapshot marker. It writes it out on all partitions. As soon as the observer sees it on one of those partitions, then it can stop, you basically mute that partition, and then wait for it to come on all of the partitions. And once it gets all the snapshot markers, it knows it's reached a consistent point. And similarly, yeah, you continue on to the next phase of computation, and you continue, write our markers, just like that. OK, so the questions that we have about this are, how do we handle different kinds of failures? So soft failures, some error during processing, or hard failures like an actual crash. Naively, if you can imagine the processor, it picks up from the last snapshot and then maybe resumes work. If it just tries to start writing to the log, well, we never actually cleared out that old state, so the observer doesn't know that the processor crashed. So it would maybe see an inconsistent state. So another idea, in order to solve this, when we restart, we want to send kind of a new marker which tells the observer that we're resetting state, and you should go back to the last snapshot. So we have this reset marker instead, which we send. As soon as the observer sees it, it's going to reset to the last snapshot, and we can continue. OK, so this is really what Kafka transactions are about. Instead of a snapshot, a reset marker, we call it commit and abort. And yeah, if you encounter some kind of soft failure, you can write those abort markers. So let's just take a very quick look at what this looks like. It's not really that different. We're processing data. As soon as we're ready to commit, we start writing markers. Commit, commit. If we have any kind of error during processing, we can abort it. There is still one issue, though, which is if we start the process of writing these markers, what happens when we crash? So if we kind of naively, when we start up, maybe we try to abort what's ongoing, well, it doesn't really work because we've already committed that data on that partition. OK, so what we do to solve this problem is we introduce a two-phase commit with a transaction log. So the way this works, you write your intent to commit or abort to the log. Then you write all your markers. And then you write some kind of a completion of that commit or abort to the log. OK, so now we can try this again. Before we write any data to the partitions, we send a message to the log saying that we have a transaction, it's ongoing, and it's including these 3 partitions. We write the data. As soon as we're ready to commit, we write that marker. Now, after that marker is, that prepare commit to the transaction log. After that is there, then it means basically that we're doomed to commit eventually. So at that point, it's safe to continue or to start writing the markers. Once we've finished writing the markers, we can complete the commit. And we can start a new transaction. We don't necessarily have to always include the same partitions. In this case, maybe we just include the first 2. We go through a similar process. Maybe we hit some kind of a error during processing. Then we prepare abort. Now we go to write our markers. And then maybe we suddenly have a crash. So in this case, we'll restart the process. And the first thing we'll do is we'll look inside this transaction log to see what were we doing before. We were preparing to abort. So that means we need to write markers. And it's OK if we write the same marker twice. There's no data in between it. So what does this give you? Basically, it gives you atomic writes across multiple partitions. And that includes consumer offsets. So consumer offsets are really just another topic. So we can include them in a transaction just like any other topic. Oh, sorry. And that's really what we needed in order to solve this other weakness. So the next one is protection from zombies. Yeah, if you want to stop a zombie, you need a fence. But first, we need to have a way to identify a producer instance across restarts. For that, we introduced this ID called the transactional ID, and this is specified by the user. So there's kind of 2 different options. You can either have the ID generated by the broker or by the server, or you can have it generated by the user. So if you generate it by, within the library or by the server, then the user is going to have to take on the burden of persisting that somewhere so that it can be reused when the processor starts back up. So we opted for the alternative, which was the user needs to tell us, which instance a producer is. So I want to take just a very brief detour from this zombie fencing problem, just because it's difficult to find a place to put this in the presentation, and discuss transaction log availability. So this pertains to this transactional ID. So the transaction log, it's also just a topic in Kafka. And that means it has multiple partitions. Each of those partitions is replicated. So the transaction log, each transactional ID is mapped to one of the partitions of that transaction log topic. So for this, we have this find coordinator request. So whoever the leader of that partition that transactional ID is mapped to, whoever that leader is, we call its transaction coordinator. So this find coordinator request is used to find it. So in this case, we're mapping to the partition 0. So the coordinator should be 1. And from that point on, we store that state locally, and all of our transactional requests are going to go to broker 1. So the nice thing about this is, you have many different transactional IDs out there. They're all mapping to different partitions, so the transaction coordinator does not become a bottleneck. You can have as many coordinators as you want because you can have as many partitions as you want. So if there's some kind of, let's focus in on this partition 0 for a second. Of course, in general, it's going to be replicated to other brokers. Now, if there's some kind of a failure here, we're going to have regular leader election take place. the producer is going to notice that the coordinator is down, maybe because it got a disconnect or something like this. Find coordinator again. We find the new coordinator, and now we can continue. OK, so I've just brought this up here because we were talking about transactional ID. Now let's go back to zombie fencing. So in order to, the actual fence itself, like in many distributed systems, it's an epoch. So the epoch is tied to a producer ID. The epoch increments when the producer is initialized. So the epoch is used on the broker to tell who is the latest producer. If we get an epoch from a producer which is smaller than what is known to be a current epoch, then we can reject it. So this is added to both the transaction log message and the data log message because they both need fencing. So let's just go through an example of how this works. In order to get the producer ID, in order to get the epoch, we have this init producer API. Start, maybe we write it to the log. As soon as we've done that, the producer gets its epoch. It's going to store it locally. And then maybe it can start doing a transaction. So in this case, we'll start a transaction. It has just a single partition. For that, like we went through that example before, we write a message to the log saying that the transaction is ongoing. And then, if we consider the data partition that's included in that transaction, this producer is now safe to start writing to it. So if then maybe this producer 1 turns into a zombie and we start up another instance, and just like before, because it shares the same transactional ID, it's going to get mapped to the same coordinator. And it's going to also call this init producer ID. And this is where we bump up the epoch. And we begin to abort. So there was an ongoing transaction, and we start the abort process. So while this is going on, before we've written any markers or anything like this, it's still possible for the old producer to continue writing to the data topic. Because that's, the epoch there is still the highest one that the broker has seen. But as soon as that marker gets in there with the incremented epoch, then that producer can be fenced. And alternatively, after the init producer ID call had returned and we got the new epoch. So in another case, the producer, maybe it wasn't writing to the data topic anymore. It was getting ready to commit the transaction. In that case, obviously, we have the higher epoch inside the transaction log, so it's fenced. So that solves us from the zombies. So let's take a look at the API very quickly. Again, this is pseudocode. We have this new init transactions, so this is really where the fencing is taking place. We have a begin transaction. This is kind of obvious. And we have this new API here. So before, we were committing offsets to the consumer. But now we need to include those offsets as part of the transaction. So we added this API to the producer to send offsets. And what you notice also is that this send offsets, also this commit, they throw producer fenced exception. So if we do get fenced, maybe because we became a zombie, we were asleep for a while, then we expect to get raised the producer fenced exception. If you receive that, then basically the only thing you can do is close the producer. You can't really continue. So again, we're gonna simplify this a little bit. Just copying input to output. So let's go through this example pretty quickly. Now we're making it transactional. So we're sending the data, sending the offset. When we commit, we write our markers. Okay, continue along like this. It could be the case that we crash. We'd only written one marker. That's fine. When we restart, we'll go through this init transactions. The last thing in the log is this prepare commit. So we'll complete it. And then we'll continue. Yeah, another case that can happen, maybe we crash just after we had sent the data. When we wake up, init transactions, again, this protects us. So we abort this transaction, and we continue. OK, so I think one more case, maybe that's interesting. OK, so let's just, yeah, I think you probably believe me by now, but the zombie case is covered. If we had become a zombie after writing the data and writing the offsets, so again, we start up a new process. Our init transactions is going to fence off both of these topics, and it's going to abort the transaction. So then we're going to continue. OK, now if we try to commit the transaction, nothing happens because we're fenced. OK, so we've mostly discussed this processor here. Let's stop there, and let's look at the observer for a minute. Observer, of course, in Kafka is just a consumer. I want to discuss what transactions mean for a consumer. In the consumer configuration, we have this isolation level, which you can configure. So read committed, only committed messages are readable. On read uncommitted, everything is readable. Now, the consumer read isolation is a little bit subtle. The first issue that I want to mention is, typically the partitions that are included in the transaction are sitting on different brokers. And when you have a transaction which covers that, there's no synchronization between the two brokers when you start the roll forward process, when you start to write the markers. So as soon as we get the marker on one partition, that data is visible. So the consumer can read that data, even though the other partition has not got the marker yet. OK, so the point is that, yeah, there's no read atomicity across partitions as far as transactions are concerned. OK, the other issue that I want to discuss, so it takes a little bit of background to understand. So broker fetch handling, Kafka's fetch handling is very performant, and the reason is because it's very, very simple. Sorry about that. Well, all we do, this is basically all Kafka does internally. So we get a fetch for an offset at a particular offset, and the consumer tells us how many bytes of data that it wants. So we look up that offset, and we find a physical file position from the log. So we have kind of this sparse index, and basically we just do a binary search on it. And then we have the file position, and all we do is we use send file to copy the data directly to the output. So we just copy m bytes of data. So we don't do any processing. Like, we don't bring that data into memory. We just copy it directly from the log. So we take this goes back to kind of the very early days of Kafka. One of Jay's very early papers meant this is one of the key design principles, I guess, of Kafka. So we take quite a bit of pain to preserve this so-called zero-copy optimization. Now, when the log contains transactional data, what does that mean? Well, in order to avoid having to do any kind of filtering on this data, which would require us to take it into memory and lose that zero copy, what it means is that we don't filter the aborted transactions. So they actually get returned to the client, and the client is the one that's responsible for filtering. So from the client's perspective, what does that mean? There's a potential issue here, which is you send an offset, let's say a fetch request at offset 0, say. You get back, you see 2 transactions, but you don't really know what the result of those transactions is. So you keep on fetching, and finally maybe you see that one of them is committed, so then maybe you can return that data. And then maybe you find eventually that the other one is returned as well. The issue is that until you see those markers, what are you doing with that data? Because you can't return it to the user until you know it's committed. So do you have to buffer it? Well, that would be less than ideal. So in fact, what we do is a little bit different. We give the consumer a hint. In the fetch response, we return the data as just a big chunk of bytes, and we also return a hint as to where those aborted transactions actually begin. So we include, in particular, the starting offset of the aborted transactions. And the consequence of that is, yeah, since we need to be able to return this reliably to the user, we say that messages are not readable at all until they have been committed or aborted. So how does this actually look? How does this change this picture? Well, when we send a fetch at offset 0, we get back that, we get back the same data plus this aborted transaction which begins at offset 2. So immediately we can return that data even though we haven't seen any markers. So this just continues along like this. Eventually we see those markers. And we can continue. So there is kind of a subtle point here, though, which I want to mention. Now, in the face of concurrent transactions, the question is, here we have a committed transaction and one which has not been committed yet, or committed or aborted. So the question is, when can we return the data from that first transaction? Are we bound to wait for the other transaction to complete first so that we can return the whole transaction, or can we return only a part of it? So, in kind of a simple case, we might immediately see the abort marker come next for the other transaction, and it's clearly safe to return all of this data. But in another case, it could be that we have another transaction begin before we see that abort marker. So sort of by induction, we could end up prolonging this process of not being able to return the data because we're trying to return it in whole. Okay, so what we do is we weaken the read semantics a little bit, and we say that, okay, we can return part of that transaction, but we don't return any data past this undecided point. Okay, so what we call the last stable offset, this is the offset such that all prior messages at earlier offsets have been committed or aborted, and everything up to that point is fetchable. Now, as we continue, as we see other transactions, as they become committed or aborted, we're able to move that last stable offset forward and see more of the data. Okay, the key point there is again about read atomicity. So there's no read atomicity as far as a transaction is concerned. So let's summarize very quickly what Kafka exactly wants semantics means. Idempotent producer exactly wants in order. Transactional producer atomic writes across multiple partitions. And the read committed consumer, well, what we're limited to saying is that you only return committed messages. So we're getting close on time. I just want to mention a couple performance observations. So if you think about now that you understand what a transaction is, all of the overhead comes at the beginning of the transaction and at the end of the transaction. When you're in the middle of it, all you're doing is producing using normal writes to topics. So you can sort of make the overhead of a transaction proportionally as small as you want by increasing the size of that transaction. But the problem is that it will also increase the latency because we do not return the undecided data to the uncommitted data to the consumer. So you have this trade-off that you need to think about. Now, I'm going to skip through this a little bit. Yeah, I limited the processing model quite kind of intentionally. So Kafka EoS is really covering processing, within Kafka. So if you've got, yeah, we were looking at this process model before. I just made it a little bit more concise. As long as you're staying in Kafka, exactly when semantics are protecting you. And Kafka streams gives you this. You just enable this property, processing guarantee equals exactly once, and you're done. But eventually, you want to get that data out of Kafka, maybe to put it somewhere else in Elasticsearch or something like this. And for that, you need some kind of coordination with that remote system. Kafka Connect already has a number of implementations of sinks which provide this for HDFS, Elasticsearch, and so on. Then the other side of this, your data doesn't originate inside Kafka, unfortunately. It has to come from somewhere. And you have Kafka Connect sources, which potentially can do this. This is still a work in progress. And in general, you still need the coordination of the source system. If you have a model which is sort of like Kafka, where you have a partition which you can track with kind of an increasing offset, you could do the same thing using Kafka, a Kafka transaction that we do with Kafka itself. But that's still a work in progress. Future improvements, yeah, we want to do something about this latency. I think this is the biggest issue. In Kafka streams, I'm not going to discuss this at depth, but speculative execution, this is kind of this idea. So you say that aborted transactions, these are probably rare in practice. So what you do is you read in uncommitted mode, and as you're reading, you assume that the transaction will eventually be committed. And then if you later find out, oh, it was aborted, well, then you do some rolling back. Okay, so that's the basic idea that we're looking at. Okay, so we're at the end. Thanks for bearing with me. This wasn't all my work. A big team did this. And the work goes back, a lot of contributions from community members as well. If you want to read more about it, KIP98 says Kafka Improvement Proposal. We have a large design document which you can read as well if you're really interested. Apache Kafka. These are basically the links if you want to learn more about it, or if you're interested in participating, like contributing or anything like this. We're always welcome to have more contributors. Ask questions if you're having problems. Let us know, and then finally, Confluent, obligatory. We're hiring. So thank you all, and I'll stick around for a while.